morning, everyone. Welcome to Pediatric Grand Rounds. It's Dr. Permashore. As always, if you are anywhere near the Tanglewood Complex, please join us in person at the Mill Mountain Conference Room. If not, thank you for joining us online. Today's speaker is Dr. Laurie Wolfe, PhD. She's the Director of Human Factors Implementation at Carilion Clinic in Roanoke, Virginia, and holds an assistant professor position with Virginia Tech. She received her PhD from Loughborough University in 2016 and is a certified Six Sigma Black Belt with over 25 years of experience in the healthcare environment. Her interests include improving safety for both patients and staff. She has achieved outcomes such as preventing accidents, increasing productivity, lowered injury rates, and reduced worker compensation costs by implementing interventions in industrial and hospital environments. Please join me in welcoming Laurie Wolfe.
I'm just going to stand here if that's okay. So, as a human factors engineer, I am not clinical, but I've just been around you guys. Everything I know about healthcare I've learned from our nurses and our doctors. So what I do is bring the engineering approach into healthcare. So we're going to learn today about what human factors is and how it can help in healthcare. This is just a little icon. I sort of introduce myself. I got my master's degree in industrial engineering at Virginia Tech. My very first job out of school was at General Motors. So I worked for advanced vehicle engineering on cars of the future. So anything the human interacted with the cars, so the controls and the displays and comfort of driving. And I did a lot of auditory displays. That's my specialty area. And then after working at GM, I moved to St. Louis, and there I worked for Emerson Electric for electronics in space. I got to work on anything the human interacted with military equipment. So I worked on helicopter cockpits, Navy ships, and I specialized in the Hellfire missile, designing control panels and helping people fire that efficiently and accurately every time. It's a very complex missile system. So what human factors does is make things easier for the human. So when I switched into healthcare, it seems like a big switch, but it really is the same principles and research that I do as an engineer, I can apply to any industry. And when I first started in healthcare, they didn't do a lot of human factors inside the hospital. And so I would go out to different industries of all kinds, like leather manufacturing plants, computer chip generations. The same principles work in any method that you do. So along the way, I got my PhD in 2016. I just part-time on the side, but I did it in the UK, and I specialized in fall prevention. So I worked on how to keep oncology patients from getting injured when they fall. They're really good at that over there in the UK. I learned a lot. So bring it back into here. So basically, human factors is anything a human sees or hears or senses and how they interact with whatever equipment it is, whether it's an IV pump or a car or a helicopter. It's all in the same way they interact. And so the human is the same. Understanding human capabilities and limitations is the same no matter what environment you put them in. So to get us up and going this morning, everybody wake up. I want you to sit up straight in your chair, because human factors is about ergonomics. And this is a game that illustrates what I'm talking about. So I want you to put your right foot out. Oh, sorry, first point at my screen. Point at the screen up here. Put your right foot out. And now you're going to turn your foot clockwise. You're going to twirl your foot in the clockwise motion, right? Like this. And now I'd like you to take your finger that's pointing, keep that foot going, twirling it. And now I want you to draw the number 6 with your finger. Now look what's happening to your foot. What happened there? Your foot, good, automatic, you don't even think about it, right? It's the same principle that happens when you are so good at doing something and you're just not thinking, you've grabbed this medication 1,000 times, you know that medication, you just look and see. Sometimes your mind and your body do different things, and it's easy to see how you can make a mistake. So we know that we're prone to doing that. So we have to design our environment to adapt to what your human brain does. The only people I know, by the way, that can do this, my son does it fine. He's a lefty, and he draws his sixes like this, inside out, instead of like this. So he draws his sixes in a clockwise motion. So he didn't think this was a fun game at all. Okay, so what human factors is, what we learn in school is everything about human capabilities and limitations, everything we can learn about people. How they think, how they act when they're tired, all these conditions about humans. And then when we go out in the real world and we try to understand what the job is like, what the task is, what time of day it is, how long is your shift, all those factors matter. And then we come up with an environment or a piece of equipment, whatever it is we're working on, to make it the most productive and comfortable for the person that's using it, and most importantly, make it so that ideally it's as error-proof as we can possibly make it. So it makes things easier to do and get your work done. So human factors is a combination of psychology, engineering, biomechanics. We take all these different sciences and pull them together with the human focus. So also it's one way to illustrate what human factors is to tell you what it's not. Human factors will not eliminate human error. No matter how good we are, humans make mistakes. Even if it's a perfect environment, because we're humans, we're going to make mistakes, right? Our mind and our body aren't always doing the same thing. So we won't eliminate error, but what we try to do is make is an environment that's resilient to those errors to prevent them from getting to our patients. We do not try to change the person. We don't use education that much, even though we do teach a lot, but we don't try to teach someone how to not make an error, because it doesn't work, it doesn't sustain. That doesn't mean education is not important and you have to learn about your products, but to teach someone not to make an error doesn't sustain. So what we try to do is make the product or the process as error-proof as we can. So just telling someone not to make a mistake isn't going to help. We also don't focus in on one individual. We look at the system. What is it about the noise and the lighting and the whole environment that contributes to that error that happened, and not necessarily what that one individual is. Then it's also a science, it's a degree. You get your degree in human factors. And then we're not all the same. We have 4 people in our human factors group here at Carilion. We're embedded in and we work elbow to elbow with our physicians and our nurses to try to make things better. But each one of us has a different specialty area. So together every Friday, we talk about our projects and try to collaborate and take the best of all of the different knowledges. So it's an advantage that Carilion has with having a larger group. We are also affiliated with Virginia Tech, so we get to do research there. We have an internship program, and it's really great to be able to do the research side as well as the practical applied piece. Another illustration of what human factors does. This is an example of an architect that designed this beautiful little sidewalk. But how do people actually use things? This is as the architect imagines the sidewalk would be used. Yep. But this is as it's actually done, right? Look at the drill field at Virginia Tech, right? It's a great example. People don't act the way you design for them to act. And so what's really important for us to know is when we go out, we try to see how work is really done, not how we imagine it's done, not how the policies are built with managers around a table, but what is it? What's the way the work is really done? And healthcare workers are the best I've ever seen at workarounds. They will get the job done no matter what it is. But sometimes that's where our risk of error is. And so what we really need to understand is what's the gap between what we think people are doing and what they're actually doing. And that's where human factors is the best at that's where we get our start, is we try to understand why they're doing the workaround and make the environment match the workaround as opposed to teaching them the right way. Because most of the time, you know the right way to do it. It's just not possible to do. So what are those barriers and how do we break those down? That's what we do. This is a model systems engineering initiative for patient safety. It's a very common way to apply human factors in healthcare, and it's just a systems way of thinking. So when we go out and do an analysis, we make sure we remember and do all these things. We've got the organization. Oh, I do have a little pointer there. So in the middle of our whole model is our person. Anyway, the cool thing about healthcare is in the very middle of our model is a person, which can be many people. It's our patient, it's the providers, it's all of the suppliers to get the supplies where you need them. So there's a lot of people involved in healthcare, which is what I think is really challenging. It gets what I love about healthcare. But we look at what tasks are being done, the environment is done in, the technology and tools, which is huge in healthcare, and then the organizational piece. So I'm going to give you a few little examples of each one of these kinds of things that we've seen out in the real world. So this one is representing the environment. Sometimes the environment doesn't match. Have you ever seen the push and pull doors? This is an example at a hospital where the only difference between push and pull is that couple of letters. So what you end up doing, if this handle is designed for pulling, that's what you do, even if it's push. So the handle should be designed for a push, like the bar to get out that door. That's a push handle. Don't try to grab it. So the design itself can cause problems. I'm going to give you a story here that also represents human factors to me, or a mismatch. What happens when your environment doesn't match your capabilities of the human that's using it? So this story comes from 1971, cosmonauts. It was a mission at the time. The cosmonauts had completed the longest space stay at the time. And they were re-entering the Earth's atmosphere after a successful mission. One of the rocket boosters didn't ignite the way it should have, and what happened was it causes a loss of cabin pressure, the air pressure. So it's the same as a scuba diving. Does anybody scuba dive? If you come up too fast in scuba diving, it causes the air pressure to you can break your eardrums. It's not a pleasant way to experience. So that's what was happening here. Is that the cabin was decompressing, but the engineers knew that that was a possibility. So they had put in a valve that was manually able to close that pressure, just in case if that had happened. The problem is when you are going through this, you have 45 seconds to live. That's because what's going on in your body. It's all of the things that's happening, and you will die in 45 seconds once you're in this decompression. So the engineers that had designed this had a valve that it's a kind of a T valve that you pull down and twist, and then release, pull, twist, release. That's the style of valve it was. And then look at the picture here. These are the three cosmonauts that were actually in Team B. Team A got sick right before the launch, so this is Team B that came in. And look how crowded it is. Where do you think they put this valve? Probably would never be used, right? The odds of it being used is very, very low. So all these buttons that were needed all the time took the best real estate. So this button was actually in this middle seat. The middle guy was the only guy who could reach it, and it was underneath his seat. So imagine with all this pressure going on, you're bending down, he's got to reach below his seat, he's got to pull that valve and twist it. So the capsule lands, the ground crew goes to see if they're going to be okay. And they haul when they open up the door, all 3 cosmonauts are dead. They haul the space capsule back in, they evaluate what happened. Why didn't they close this valve? The valve was halfway closed. So these guys fought as hard as they could possibly fight in an environment that wasn't matched to the capabilities that they had at that time. So this is kind of a dramatic version of a mismatch between environments, but it does show you that it matters. You got to understand the situation that when you need those controls, what it should look like. So in healthcare, not all of our things are so dramatic, but this is an example of a mismatch where you can't see the contrast. See, there's an image there on the window, nice and marked, so you can find your way around, but when it's glare and white letters on a white background doesn't show up. So this brand new building ended up putting these dark blue circles, there's patches over there. If you see signs, patches, Post-it notes on things, it's because usually the design isn't matching, and that's one of your signs for workarounds. So that's what, if you go around the environment and look, not only watch how people are really doing their work, but look for these workaround adaptions, and that's what we try to fix. So in understanding, in addition to the environment, well, if we understand human capabilities and limitations, they're both physical and mental. This is an example of physical demand. Those of you sitting here or even at home, put your arms out like this. If you have this extended reach, you do that a little bit, it's not too bad, but if you have prolonged extended reach or you're lifting weight, heavy weights there, it can get fatiguing. So how often do you think you have that position? Some of our jobs in the hospital does require extended reach or holding a retractor for 45 minutes. That's physically difficult to do. And we also have mentally fatiguing issues in the hospital too. And all these things are contributing to leading up to why we make errors. This error actually happened where this is a medical device that requires you to scroll through several screens to select a medication. And what happened was they got to screen 3, so they're already scrolling down 3 screens, and look at the medicine that's at the bottom was not what they needed, but it was on screen 3. What they should have done is also scroll to screen 4 and pick the same medication with a different dose. So what happened is the patient got the wrong dose here. But you can see why that happens. So you're in a hurry, you've already scrolled through 3 screens and you go, oh, that's the medicine I need, and you grab it. So in my opinion, we could have done this better by putting the same medications on the same screen. It might make you have to scroll even more, but there's other ways of avoiding scrolling too. So I don't even like that whole concept, but if you have to click, click, click and scroll, you know that from using the medical records. There are ways you can design this to prevent or make it a little less risky. Okay, I'm going to play another game. We've got a lot of games in here to keep us awake today. So this game, what you're going to do is I'm going to show you some lab results. It's actually from a veterinary clinic, but I'm going to show you some labs. I'm going to give you a minute. I want you to tell me how many lab values are outside of the exceeded limit. Okay? Everybody ready? I'll give you a minute. Oh, now, interruption. How many times are you doing the task and you get interrupted? Someone asks you something or your attention's diverted away, right? So you didn't get to finish. So we're going to give more time. When you have more time, what I did, you're mentally thinking over here. Now you've got to reset yourself and remember how many did I get through. And so it takes you, they say on an average of 10 seconds at least, once you have an interruption, before you can refocus your attention. And depending on how in-depth of a mental load that is, sometimes it can be 45 seconds before you actually get back and re-engaged. So if you're switching from one patient to the next or one thought, even a conversation, that's an interruption to get you prepared for the next patient. It might be information you need for the next patient, still an interruption. And every time we're interrupted, we risk a possibility of making an error. Okay, so there you go, back to normal. Okay, and really the point is, we could do better. So I can say, well, how many people found what? But really, if this is what the layout looked like, you could do it in less than a minute, right? Mm-hmm. And if you got interrupted, you could just go back and look at what's outside of the norm. And then what human factors always tries to do is improve on that. So I like this format better, but could we make it even better? What if it looked like something like that? And then what this does, though, is makes you rely on that visual aid. So that's also things you have to balance in understanding the whole thing versus just relying on an outlier. But this is one way you can fix it even better. So moving on beyond mental and physical capabilities, sometimes it's just the perception and how our bodies work. So we have auditory and visual limitations as well. So just one example of visual capabilities. Humans, we know, see better in this 30-degree cone of vision. So ideally, anything that I want to look at can be right here without me having to move to look at something, right? I don't see things and process it as well when it's outside of my cone of vision. So examples we see all the time, every day, that exceed our capabilities that get outside of our cone of vision. Does it happen in healthcare? All the time. Here's an ICU. And then this also has an auditory component too, that's, you're visually overloaded and auditory overloaded in a lot of cases in healthcare. This is a project that we did to try to understand some of this overload in our remote telemetry. This is where we started a new way of monitoring telemetry in a remote location. So ideally we can do monitor more patients. Our monitor techs are required to do usually around 30 to, used to be 36 patients during the day. And so you can see within this cone of vision, they can't see all the patients at one time. So these are, over here on the left is a monitor where they have the electronic medical record. So they have to identify a problem, call someone, and then document it in the medical record. So it's a very visually taxing task, and they sit there for 12 hours a day. So we did an experiment to simulate their task for 1 hour, and we wanted to see what kind of responses they had and how accurate they are at doing this very visually overloaded task. So in this 1 hour of alarms that went off, we simulated the same number of alarms and everything, and had actual people come in and sit there for an hour and do our study. We found that on average, this is our response time. If an advisory alarm all as visually complex as this job is, some of the alarms didn't have an audible component, it was just visual. So if it was a visual alert, it took them 13 minutes to recognize that needed a response. If they added the auditory alarm, that was better. They were like, if it was a medium or warning alarm, it was over 30 seconds. But the good news is, if it was really high, like a code blue crisis, they did recognize that successfully, accurately, within 9 seconds. But overall, their accuracy was about 50%. But for the very critical alarms, they were good. So then we also measured their mental workload. That's another thing that human factors can do in usability studies. We look at it's a way of rating mental workload, and it was developed by NASA, but this is a version for healthcare. And we can tell whether what component is particularly stressful in mental workload. And in this particular 1-hour study, we found that time pressure was one of the hardest things, and then the mental workload. So, and it kind of makes sense. They were just sitting there, so physical workload was pretty low. But it's a way that we can tell how to go back around changing things. So we need to change something about how many things they're balancing on their mind at one time. That's the mental piece, and try to reduce the temporal part by maybe reducing the number of alarms. There's 146 alarms that go off during this 1 hour, on average, 1 hour every 12, and they do that times 12. It's a very stressful job. And then I mentioned usability. That's something we do quite often, is study how useful a product is. So sometimes a product looks nice, and maybe it's even what the customer wants, but when you actually use it, it's not very effective. So here's some examples we've seen in healthcare. Oops, this is another game, okay? Another game that's going to show you how we can predict what you're going to do. All right, ready? All right, what did you do there? How many read the big banner first? Yeah, we set you up for failure on this. Again, because humans read from left to right, it's predictable. We know that if you put something big and flashy in your face, that's what you're going to read first. We also know dark backgrounds aren't as good. So there's all these things that are just predictable heuristics that we know about humans, and this sets you up. And then if you did read that last one first up there, there's actually a mistake, and you will this read last. So we even made an error. How many people caught that? We also buzz over words and we don't read them very well. So this is really important when we're trying to establish BPAs or arrangement of our medical record. Think where the patient name is, one of the most critical things to get right on a medical record, right? It's up there in that corner that you don't really see very well. Okay, this is an example that we found in the OR from a retained object. A guide wire can feed through, and if it escapes, I brought an example to show you. You can feed this wire through, and it just slips right on out. And so what they do is they teach you to hold on to one end of the wire, right? Which is great. You really need to have education for this product. But there's times when there's a lot going on, or you need your hands and it slips through. So this is a never event, they call it, yet it does happen. And we can see why, because this just slips right on out. So we had our innovation guys come up with this 3D printed version. It looks pretty much the same, but when you feed this out, it stops, and it is impossible to feed it out without grabbing the end. So it forces you to hang on to that end before it comes out. So this is what human factors is trying to error-proof things. Now, this is just an idea that we have, and we're trying to get the manufacturers to do something similar like this. But human factors in our innovation team are always trying to come up with ways to produce products that will be error-proof as best you can. It's still not totally wrong, because you got to get this wire out. It's the way it works. You have to get it out of here to do some other parts to it. But at least it forces you to grab onto the end of the wire before it feeds out of there. This is another one we tested a couple years back, and now there's actually been a recall on this intubation thing. It was in pediatrics especially, the patients were getting extubated by accident because they're flailing around. And so we just measured how much force does it take to get this tube out. And we found if you flail around a couple of times, by that third time, it's really easy to pull out. And now this is actually being recalled. So my message here to you guys is call us. We have to understand you guys are out there and you see this stuff every day. So if you see something that's either makes your life difficult or doesn't make sense, that you want to change something, call us and we can come out and take a look at it, see if there's something we can change. So So I have a couple of examples here. I gave a presentation to the dermatology residents, and they called us up and we came out there. We looked at the work that they had to do in their small space. They had a shelf. See, they can't even lay the patient down because the shelf was in the way. They needed the patient to be flat. So they couldn't even get the patient in the position they wanted. This shelf in this small little room came out by 15 inches. So they were very limited in where they could position the patient. They also had this great big light, but the light wasn't shining where they needed it to be. So they're reaching down and trying to evaluate parts of the patient, but it would actually create a shadow. So what they were doing is using their cell phones, holding with one hand to get a light where they needed it. So we measured the lighting at the point where it's needed on the body, and we found that it was lower than it should be. There are, again, what we learn about human capabilities, if it's a very fine inspection task, you need 50-foot candles. That's the science that's out there in order to read accurately or identify things. And some small detailed work even needs more lighting than that. So it should at least be 50-foot candles for this situation, but we found it down as low as 9-foot candles. So, and even less under some, in some situations. So anyway, the light, even though it was great big, I think I have a picture of that. Yeah, there's the great big light that's there, but it's not flexible enough to get where it needs to be. And it bumps people's heads. So there was all kinds of problems with the light. If you put the light up where it's designed to be, it was fine, but it was just that it's not flexible enough to get where it needs to be. So whoever put that light in didn't understand the tasks and the nature of the work that's being done by that dermatologist. So we were able to make a few changes, not perfect, but they are a little happier with their environment than they were. We're still working on this kind of ongoing project. Okay, this is an example of a BPA that the electronic medical record is going to give you. This is the version over here is what they were proposing. This is how our IT people wanted to do it. They spent a lot of time on this logo, which is great, but it doesn't provide information that you need. The lab results were right down here, and that's what you really needed to see. And the number one thing on this BPA is that button. And so the human factors people and physicians sat down together to develop what do they need from a BPA. And what they really wanted were these lab values, and they wanted to know the most recent ones in a sequence like this. And so by sitting together, getting people the information they need, this is a little more usable than it was. Now, there's still constraints because we still want to be able to hit that button, but at least we were able to put the buttons in one place. So again, it's refining it, making it a little more useful. And this is around sepsis. It's important. And then sometimes we have policies, so this is the work as we imagine it to be. We were getting some errors. People weren't doing the process the way that they were supposed to do it. And if you look down on page 19 of this, if you can find the policy, it's several pages down. This is what it looked like here on the left. So the policy is still 19 pages, but what we were able to do is to make it a little more clear, simplify the process. So still, again, not perfect, but the tool that we use to do that is hopefully a little bit better. So even if we get an environment that's ideal and clear and the rules are known how to follow, it's human nature to drift towards riskier behavior. It's just what we do. If our processes are too long, we end up shortcutting them and finding easier ways to do things. And the problem with that is we can drift to risky behavior. So the easiest example I know that we can all relate to is the speed limits. But So I think everybody has probably exceeded the speed limit 55 if you're out in Nebraska and you're going for 10-hour drives, just driving. There's not a soul out there. Easy to see how you can drift to that behavior. But if you're using risky things, like if your environment is the MRI and you're used to that risky kind of environment, or administering chemo drugs or something like that, again, it's easy to see how you can drift because it's just your normal behavior. But we're also good at adapting if we're in a school zone, say, and the speed limit is 25 or even 15. Sometimes we don't even go that fast, right? So we do adapt based on the situation. So taking what we know about people, what we try to do is error-proof what we can, make it as strong as an intervention as we can to try to prevent errors without humans having to think about it. So here's one example here is the trays were getting lost in the cafeteria. And so just by making a hole that the tray won't fit in, will keep them from getting thrown away. So that's great, but again, we can make it a little bit better because you can put it on a diagonal and it still goes in. But if we made it round or something, maybe that would even be better. But this red arrow is representing things on the left that are based on human behavior to get it right versus on the right here is the system is error-proofing it for us. Anytime we rely on the human to do the right thing or to educate the human, we are at risk of that drift, behavioral drift, and we're at risk for errors because people get tired, or even highly trained people that have done the same thing perfectly over and over and over again. The nurses grab that medication 1,000 times, have given insulin. It might be the time that she's tired, and maybe the lighting is wrong, and the nurse can grab the wrong medication. It happens. It's just, that's called a skill-based error, and there is nothing to do to prevent the skill-based error. You can teach all you want, because it's not a knowledge-based error, but it's a skill error. And the people most at risk for skilled errors are the most experienced, most educated people, because you've done it so many times. Oh, I should have had this slide up. So the kinds of things that we do in healthcare, oftentimes if say an event happens and we do a root cause analysis and we figure out how can we try to make this never happen again, oftentimes we educate or train people, right? How many times does that happen? Yeah. Oops. Checklist, double checks. That's how, for high-risk meds, we have the nurses double check each other. It's still people focused. Those are always going to be on the weaker side, as opposed to a forcing function. I'll show you some examples over here. So we always try to come up with some kind of strong intervention when an event happens. So this is an event where the portable ventilator went in the MRI machine. In this particular case, the portable ventilator was supposed to be there, so you can't keep it out of there, but how can you keep it from going into the roof? And so we did a big root cause analysis. We did a fishbone diagram. We did the 5 whys. These are all the process improvement techniques we use to try to figure out what happened. And we came up with these possible interventions, 6 different interventions, some of them weaker, some of them stronger. Yeah, picture that. Yeah, so here's our same old error. These are our human-based interventions. So yes, we did retrain everybody about the zones going into the MRI machine and how careful to be in zone 4. So we did that. We did make sure our room layout was where it was and the markings were where they needed to be, but those are on the weaker side because humans have to do what they're supposed to do for that. So we came up with a stronger intervention by just tethering the ventilator to the wall. And that was okay, but we wanted to go a step further in strength, and we actually bolted it to the wall. And you'd think that was it, right? So I, for a couple of years, was saying, this is the strongest intervention, it's bolted to the wall. That works until it doesn't. There was a time when the maintenance had to change the battery on this thing, and there was no one around to find a key, and they have their limitations, their requirements to get their job done in a certain time. So they get a crowbar out and they're trying to get into the box. So then we, again, made it even harder to get into. So you always keeps trying to make it more and more error-proof. This is another example where we were trying to make the crash cart more efficient. We need to get things as fast as you can. And we had done some lean engineering work on it to get all the things in there that only the things that are required to be in there are in this thing. So some of this had already been sorted out, taken the unnecessary things out. But what we did in human factors was to figure out the optimal way to arrange this cart. And so what we did, I think I have to do this. I have a video here. We did this in the Sim Center and reenacted a code. So this is a code where the cart is needed. They bring the cart in. This is this person on the right is acting as a physician. On the left is the nurse that is trying to find Narcan. So that's her job while the doctor and the code team are doing their work. So you see what she's rummaging through. We videotaped it. We looked at everything she touched and moved. She's searching for Narcan. Notice this piece of paper up here, because that has the answer on it. That tells you right what she needs to know. See what she does with that paper? She doesn't read the paper. People don't read signs. They don't read those. So it needs to be organized in a way that makes sense to her. She's still searching for Narcan. She's having to read these things. Is the lighting good enough? We know the font is really small on those bottles. We know it's written on a curved, but reading a curved surface is also very misleading for things like O's and zeros and sixes and eights. It's so easy to see how we can make mistakes. So she did finally find her Narcan, and we made recommendations to change it. So this is before what it looks like with the piece of paper versus after. So we just put them in a place where they needed to be. And there's our Narcan right there. And then we refine it as we go. We have people come back and do it again, and we revise these as we go. But just to give you a feel, the very first time we ran this, it took 84 seconds. After our final redesign, we cut the time in half and the number of motions and physically finding things in half. We made it better. Could probably still be better, but at least it's a little better than it was. Okay, I have one more example to show you here, and then we'll just stop for some questions. Sometimes we can do things, predict where errors are going to happen before they're ever built. And so this example we did right here in Tanglewood. We've done several of these now, but if we could reenact a blueprint full size. So we work with the architects, and they'll usually come and show you the blueprints and say, hey, is this going to be an environment that meets your needs? It's really hard to tell that off of a small blueprint. So we build a life-size cardboard mock-up. We bring people in and reenact the scenario that they need to do in that space. And so usually it's a typical scene, like a regular exam, say in the ENT space, or sometimes what happens if the patient codes in an exam room? Do you have space? So that's what we did here in this. This is the environment. This is the fake patient here. The patient's coding. They bring in a crash cart. They're starting on the piece of paper as the patient. And what we do is we track them on video. We put a GoPro up at top, and we track where everybody moves. We have different colors for different people. Watch, EMS comes in here. Watch what happens. There's a sink on the wall. Sink gets knocked off. And so we analyzed this by by motions and crossovers, and we've done this for the trauma bay in the Crystal Springs Tower. So we do several of these kinds of projects, and it helps us understand how humans behave in the space. We're able to make changes to the space itself, as well as it gives the people a chance to come in this new area and understand what it's going to be like. So it relieves the fears. So like in the trauma bay, it was a different size that they were used to, and they were worried they couldn't do what they needed to do in that space. And here at Tanglewood, this is one of the spaces, we were worried that it would be too small to get some of that work done. And sure enough, that sink is in the way. We track the motion and the crossing. We also track bumps, how many things bump into each other that shouldn't bump into each other. So we can freeze frame it, and you can see this, here's the provider trying to get to this piece of equipment. The family's there in the way. This is the patient. This is before versus after. We put the family in the far corner on the opposite side of the door, so the provider has good access to the door, and the family's not in the way. So this is what it looked like before. There's our sink. There's our family area there. And so this is what we recommended based on the evaluations that we did. We wanted to put the sink in the far corner. We wanted to put the family here. This is our biggest change, I guess. We did get the family in the corner, and that's what you'll see here in Tanglewood. The families are in the corner space. And we didn't get the sink where we wanted it because there's lots of constraints that we don't always get to control. But the architects were at least able to put the sink over there as opposed to here. So it gives you a better access. If you do need access, the sink doesn't get knocked off the wall. So that's the end of my examples here to show you. Wanted to save enough time for questions. Humans will make mistakes, always. Listen on the news, how many times you hear human error. There's been a lot of plane crashes and things lately, and you hear human error attached to that. So whenever you hear human error, that's where our job starts. We're going, why did that human make a mistake? In all the years I've been doing this, I've never once had an intentional mistake made. Nobody's intentionally trying to harm patients or crash their planes. There's always something, a systems reason why those things happen, and all the Swiss cheese model where things line up to make that error occur. But it's not the human. The human's acting like a human. You're doing your foot twirl, doing 3 things at one time. So if you hear human error, keep looking. Anybody have any questions?
So with electronic medical records, we talked about other issues. You talked about alarms, alarm frequency, alarm fatigue, and are there initiatives to use that data preemptively to look at reducing alarms, reducing keystroke, increasing efficiency helps preserve attention. And in setting up some of these fail-safes, you increase the number of clicks, you increase the number of stops. And when you stop, just like you said, you have 10 seconds, you got to regain your attention.
Yeah, that's a brilliant suggestion. Really, a lot of what we need to do is reduce these interruptions. So if you do have a BPA, that example was hopefully if you are interrupted, you make it a worthwhile interruption. But overall, like the telemetry operator has 146 alarms, 30% of those, the correct thing to do is nothing. So why are we even giving them an alarm? Giving them an alarm when they need to do something. It's same with the BPAs. There's so many BPAs, we've got to start reducing those. There is a team that's trying to reduce some of those unnecessary interruptions. Because many times, when you're in an event, you're saying, oh, let's add a BPA for that. But it just becomes noise and you don't pay attention to it. That's the best suggestion, I think, is trying to make things as simple as we can.
And your discussion also emphasizes how this kind of, particularly dealing with physical spaces, you think about virtual space as well, but physical spaces, you need to have, when you're setting up a new process, a new space to use, that this kind of thought process needs to begin in the planning stage.
Early.
And have all stakeholders involved, including those who are controlling the budget. Because yes, you say, okay, it's expensive to reroute the piping for sink and all that, or that was a pretty expensive MRI machine to have a ventilator go flying into it with a patient on it. So, yeah.
We had an example, it's a small example, but it happened here in Tanglewood. When we did that example, we had the physician work surface, and we wanted rounded edges because you got those children coming in, right? Mm-hmm. Well, then COVID hit. We weren't involved after that. We sent a list of features that we wanted to the architect, but I don't know what happened between that list of features where we had a rounded edge and what was actually purchased and installed. And I'm only guessing, but it could be that a square edge table was cheaper. I don't know. But then, I don't know if it was 6 months or a year into it, we had a few injuries from toddlers hitting on the sharp corner. And so from what I heard, I should go and look, I've heard that they retrofitted.
Yeah, we had to retrofit all the tables. And
so what's that cost? You know, that's direct costs that we shouldn't have had to do.
And in this room, probably every single one of us recognized that when they did our quote walkthrough 4 weeks before opening.
And we recognized it before that was even purchased. That was one of our design features, was a radius edge on every corner.
You know.
Yep. But
every situation is
you know, there is
critical.
Yep, there's pros and cons,
issues,
right?
Yeah.
There, someone might have been saving money, I don't know.
You have to have the ability to say, we need to stop this right now, rework it before we have these.
I totally agree. And I do feel pretty good about some of these architect things we've been able to get involved fairly early. Never early enough, but the earlier we get involved, the cheaper it is to make changes. And what we are good at is getting the right people. Because again, we only know the process. We're not clinicians, but we know enough to know to get this person with this expertise and this one in here, and you get them all in that cardboard space, and then you get everybody's opinion. Thank you so much. Okay. Thank you for listening.